to talk about cold boot attacks on DDR2 and DDR3 RAM. So this was a joint work done by three persons, which is first of all Simon Lindenlauf, who is has been a BSc student at Aachen University of Applied Sciences, and he's now a master's student there. Then myself, Markus Schuber, as has been mentioned before. I'm working there as a professor, teaching and doing research in the areas mainly of security and digital forensics. And then third member of the team was Hans Höfken, who has given the presentation yesterday. And he's also a researcher at Aachen University of Applied Sciences. And he always claims that he's doing the real stuff, the practical parts, while I'm more the theoretical guy. Well, he's probably right to a certain extent, even though I also do sometimes some hands-on stuff. Okay. Who has heard about cold boot attacks before? A few of you. So this is then quite new probably to most of you, and therefore I'm going to explain a little bit about cold boot attacks before I go into the details of what we did. So after that after this brief introduction to cold boot attacks, I will briefly summarize what has been done by others so far, because we are not the first ones to do cold boot attacks. I will describe how we did our experiments. We'll describe the results that we achieved with those experiments, and finally give some concluding remarks, including also some advisory on what you can actually do to prevent cold boot attacks on your machines. Okay, this is all about RAM, and in particular dynamic random access memory, short DRAM, which is one type of RAM that is out there in the market. And the basic idea behind is that you have to store, of course, zeros and ones, bits and bytes in it. And this is done by storing each bit actually in a separate capacitor inside the chip. That means you have two states there. Either the capacitor is charged or it's discharged, and then you have two options for 0 and 1. And this is how the bits are stored in there. Since this is working with capacitors, there's one tiny problem, because there's a certain leakage in the capacitors. That means they discharge over time. So what you have to do in order to keep the state, you have to refresh them once in a while in order to keep the current in the cells. So this is also why this memory is called dynamic, because it behaves dynamically over time, and you have to refresh it every once in a while to keep the data in there. If you look at the computers nowadays in the market, then DRAM is actually the main memory in computers today. So this is due to the high density you can achieve nowadays on those chips for a low price, and compared, for instance, static RAM, that's in many cases the better solution. So we are looking in particular at DDR as DRAM, which is double data rate synchronous dynamic random access memory. You can read it at the bottom if you like. And there are basically four types of DRAMs for that. You have DDR or DDR1, then you have DDR2, DDR3, and since last year there's also DDR4 in the market. So they differ, of course, in many aspects, but the main difference from a user perspective is that they have different peak transfer rates. That means basically you double the peak transfer rate with each generation, so making those chips faster and faster. So what you see in the market today in most of the computers, so if you would open your laptop or your desktop, you will probably see a DDR2 or DDR3 SDRAM in there. And here you see in the picture below how you plug that in. I guess most of you guys are very familiar with this because you have opened up your computers. So coming back briefly to this leakage of the cells, because this is a problem and therefore we have to refresh those cells once in a while. And the question is, how long do the cells keep their state actually? And there are specifications from the manufacturers what refresh times you need for the different modules. And if you're working, for instance, for temperatures up to 85 degrees Celsius, then you have a specified refresh time of 64 milliseconds. That means every 64 milliseconds to give power to your module so that all cells are refreshed again. However, if the temperature increases, if you go, for instance, to the area between 85 and 95 degrees Celsius, then the specification says you should do that every 32 milliseconds, not seconds, I'm sorry, milliseconds. And this leads to the conclusion, obviously, the leakage increases with the temperature in the cells. And it has been shown in experiments, for instance, that this 64 milliseconds, which is the standard refresh time for the lower temperatures, with that you're actually in many cases much on the safe side. Because, for instance, tests with DDR3 have shown if you are operating at 45 degrees Celsius, which is much longer, then the retention time, so the time until all the cells lose the data, is higher than 1.5 seconds. So it takes quite a while for the cell to lose their content when they are not powered on. And this gives the idea, of course, for us, okay, if we want to keep data longer in the cell after power has been disconnected from this module, then we can cool the chips, and then we can reach higher retention times. So what is cold boot then? So cold boot is not, as you might initially think, about cooling the chips in order to increase retention time, but cold boot is simply a term which is used in many other areas of computers too. So basically you have two options for rebooting a machine. The first one is cold reboot, also called cold boot or hard boot, and then you have a warm reboot, also called soft reboot. So I have simplified that a little bit because there are many definitions out there about warm reboot and cold reboot and all the details. So very simplified, a warm reboot is simply restarting the machine while it is still powered on. That is, on a Windows machine, you press Control, Alt, Delete, and then you press Restart. Or on a Linux machine, you can have the kernel execution for commands and restart the Linux machine. But then you can also have a cold boot, and that is restarting a machine from a powerless state. That means you disconnect the cord, or even if you have a battery in there, the battery from the machine, and start the machine again. So you powered it off completely. So what is a cold boot attack then? So the basic idea behind a cold boot attack is that, okay, we have seen that you can still get data out of the chip, out of the memory chip, after power has been disconnected. And we have also seen that it's very likely that the lower the temperature, the longer time you have actually to disconnect this RAM module, and you can still find data in there. So the idea is actually to power the chip off and then power it on again and see what data is left. And you have actually two ways to do that. So if you want to dump the memory from a RAM module, you can do that in two ways. Either you can do that on the original machine, like I would power off this laptop, would power it on again and try to read out the data, or I could move it to a different machine. So I take out the module here and put it into a different machine, start up the different machine and read out the data there. Why are we doing all this? So the main purpose behind all this is actually recovery of hard disk encryption keys. So and that's a case which sometimes, for instance, digital forensic investigators are faced with. So either you are, for instance, such a forensic investigator, you might also be a criminal who would like to recover a key from somebody's machine. But in any case, so the situation would be you're facing a running machine which uses hard disk encryption. If this machine is not screen locked, then it's simple to do. So you can use normal forensic tools in order to extract the hard disk data while it's open, and you can access it, and then you extract all the data, save it somewhere safe, go back to your lab and analyze it. The problem is when the machine is screen locked and you don't know the password. So you might be at some suspect as a criminal investigator, and that suspect doesn't want to give you the key or the password to actually unlock the screen. So in that case, you cannot simply copy the disk because you have no way to get onto the computer to make all the copy commands. On the other hand, you also cannot simply shut down the machine because you could then, of course, take out the hard disk, but then it would be encrypted again, and then you would have to break the encryption in order to get to the data. What you still know is that the decryption key is usually in the RAM. So you could actually look into the RAM and take the key out to later on decrypt the key. But as the screen is locked, I mean, you also cannot get to the RAM image. So you have to find some other way. And there, cold boot or cold boot attack may still help. Because you could use this attack to provide an image of the RAM. This might contain errors depending on how much time it takes, what the temperature of the RAM was. But still, it has been shown that even though there are errors in the RAM image, you can still, in many, many cases, recover the keys. Because you do not only take the key as such, but you also have round keys stored in them, and then you can have some clever algorithm and find out the original key again. Okay, so much about cold boot attacks in general. So what has been done by others so far? So there was a very famous paper by Alderman and al., published in 2008 at the USEC Security Conference, and it was titled Lest We Remember Cold Boot Attacks on Encryption Keys, and they investigated DDR and DDR2 SDRAM. And they visualized the effects quite good by using a Mona Lisa picture, and you see on the left-hand side a picture where almost no data was lost. And then over time or at higher temperatures, more data is lost when you are using a cold boot attack. So you see some errors in the picture. And the more you go to the right, the more errors you see. So in 2013, Grun and Müller had another paper on the topic, and they investigated 3 different types of SDRAM, namely DDR1, 2, and 3. And what they stated in their paper is, okay, we could not reproduce cold boot attacks against modern DDR3 chips. So they were successful on DDR and DDR2, but not on DDR3. They had similar pictures in there. So again, Mona Lisa. And you see on the right-hand side, this was under normal operational temperature of 20 to 25 degrees. And under the pictures, you see how many seconds they had a power cut. And you see the more time, the longer the time period of the power cut, the worse the picture they got out of the RAM. So we were thinking about, that was actually on the pile of projects to do at our university anyhow. So we wanted to do some cold boot attacks and see if it works for us as well. And we also wanted to know, is it really not possible to get something out of DDR3 RAMs? So we were thinking about, okay, what could we do differently than they did before? And obviously, we could use a different picture. So as a computer scientist, I mean, Mona Lisa is not a typical picture to use. Of course, if you have worked in computer graphics, you have come across this lady probably. So maybe the computer likes more pictures that the computer scientist likes, so we changed the picture. Okay, that was of course not meant seriously. So maybe something else. So maybe there was a limitation to the mainboards that were used. And so we had some other mainboards that we took for our experiments. Okay, before I describe that in detail, first a step back and let's see how we did our experiments. So if you're looking at a cold boot attack, you have to do, before you consider doing a cold boot attack, you have to think about what you have to consider, what is actually influencing the results. So first of all, cold boot attacks depend on the DRAM type you use. So obviously there was a difference between DDR1, DDR2, DDR3. So we concentrated in our research on DDR2 and DDR3 RAMs. So then there might be differences when it comes to DRAM manufacturer. So we tested 7 different manufacturers. There might even be differences for individual DRAMs. So we investigated 16 different ones. These are the modules we used, and you see on the left-hand column that it was mainly DDR2, but also 5 DDR3 modules. Different manufacturers, different module names, of course, different capacities, different frequencies, and different production dates. Okay, then we used 2 different mainboards. So they are shown here. On the left-hand side, you see a combo mainboard, which can be used for DDR2 and DDR3. And also we used a notebook from ASUS with a respective mainboard in there, which is can be used for DDR3 only. So then there's this feature called multi-channel. So if you have multiple DIMMs in the slots of the computer, then multi-channel can be enabled or cannot be enabled, so which actually distributes the data over several of those modules. If that is switched on, then this has several impacts, of course, on the analysis of the data. And we decided that since we just wanted to investigate if it works at all, to keep that out, so we only used single-channel mode. Then we have the influence of the temperature, so we tested at different temperatures. There's an influence of the time without power, so we tested also different ones there. And then, for the cold boot, we have actually to have a new machine starting up with a DRAM where we want to read data from. So that means, of course, our operating system that we load into the memory, also the program to read out data from that memory, impacts the data that we have, what we actually would like to analyze. So we took took an operating system with a very small footprint. So the procedure then to actually execute the attack was as follows. So first of all, we had our original machine where we have the test data on, and we prepared it with test data consisting of this picture of Lena and also some 100 megabyte file with random data on it. Then we had to prepare the cold boot machine. Could be the same machine, but also could be a different one. We had to have a USB stick to boot from and to read out the data and to connect it to the cold boot machine. Then on the original machine where we have the module in, we have to adjust the temperature on the DRAM to the temperature we would like it to have. So we wanted to test from minus something degrees to plus something degrees. We adjusted that. We then power the original machine off by unplugging the cable. If you're using a notebook, of course, it makes sense to take off the deck or remove the battery beforehand. And then we have to think, are we doing the cold boot now on the same machine or on a different machine? If we are on a different machine, then we, of course, have to move the DRAM to the different machine. We power on the cold boot machine, booting from the USB stick we have prepared. And then the program on a USB stick reads and stores the RAM data. And we can analyze this offline in the last step. So to make it short, we have a couple of steps: prepare the data and the USB stick, cool the DRAM, power the machine down, move the DRAM maybe to another machine, power that one on again, and read the data out. So those steps were not all quite easy. So we had to take care that we do it right. So for the test data, we had to make sure that we have really the same data in memory for each test. So for that, we used a very small operating system to boot from the USB stick, which is based on James M's kernel development tutorial and the grub bootloader. We had the test data prepared of the Lena image, and this we only used to have a visual, being able to have a visual evaluation of the results. And therefore we only took the pixel, which are actually the picture, out from this respective image file, but left the metadata out, because if you would have put the metadata as well into our RAM, then these might have been damaged as well, and we couldn't have a look at the picture afterwards, so we concentrated on the pixels only. And as I mentioned before, this 100 megabyte test file, which we put on the RAM. Secondly, preparing the USB stick for the cold boot. So for this we used two small footprint operating systems. They were both roughly 2 megabytes in size. One is called MS RAM Dump from Wesley McGrew, which is a 32-bit operating system. That one we used predominantly because it had a good feature that on a single USB stick we could do multiple tests. It had several partitions and it wrote the data to several partitions, so we didn't have to prepare the USB stick for every experiment. The other one was BIOS MEM image from Princeton University, which is a 64-bit operating system, and that one we could use for DRAM, which is larger than 4 gigabyte. What both of those operating systems do when they are cold booted from a USB stick, they simply dump the RAM and save it to the USB stick. So for the MS RAM dump, we slightly modified it to extract the test data only, because it always wanted to dump the complete memory, but our data was only in the first 500 megabyte of data, so it was fast and sufficient to concentrate on that. Okay, how to cool the DRAM then? Any creative ideas from your side? What could you do to cool a DRAM? Sorry? Freeze it. Yeah, so we had some brainstorming on that, how we could actually do it, and we came up with some very creative ideas. This was the first one. So we talked to the dean of our university, because we had a very important scientific project and we wanted to go the Alps for 3 weeks with 3 persons to do our experiments, but that was rejected, unfortunately. So we took a more cost-efficient solution, which is simply cooling spray. And if you apply this to the RAM, it somehow looks like that. So the RAM really gets frozen. You're at minus 35 degrees, for instance. Okay, in our procedure, we then had to check the temperature, because we wanted to know at which temperature we actually did the test. And at some point then you have to power down the machine, you have to move or leave the DRAM where it is, and you power on the machine again. So we had to measure this time. And I had the impression this morning during the first presentation that you also did some cold boot attacks here on on the area because of the power failures all the time. So that would actually be a good time now for dramatic effect to have a power failure. Okay. Last step is reading and analyzing the data. So we power the machine on, and then we get some data out, which is basically some hex dump, which we get out of the chip. And then we can decide how many bit errors or byte errors did we have there. So we wrote a small script for that, and then we analyzed what we got out. For the images, we also reconstructed them and viewed them so that you have a visual evaluation of the results. And this is what it first looked like. So we saw most of the picture, but in certain cases, we just had kind of black stripes in it. And this was the result we found out because some bit errors changed the bytes in the pixel area to either the quote character or the null byte, and both of those actually caused the program not to display the image correctly, but it deleted the complete line of the picture or damaged the complete line, which was, of course, more error than there actually had been. So what we did to correct that is that we changed one bit in those byte errors. So we changed the null byte and the quote character by 1 bit, so we still had a visual representation of the actual error situation. Okay, this is a short video on how this all looked like. So what you see here on the screen, can you see my pointer? Yeah, the mouse pointer, okay. So what you can see here on the screen is a already prepared laptop computer. This is a USB stick from which we loaded the data into the system. It's still connected to power. The picture of Lena is copied into the memory at a certain offset, and then we have a 100 megabyte data file with random data, always the same, of course, for each test, written to another area of the RAM. Okay, and then the whole thing is started. So the machine is prepared. So cooling sprays is, by the way, Simon. So here you see the DDR3, and now he's just cooling that one down. When I first saw that, because I'm not an electrical engineer but a computer scientist, I was a bit scared because he was pouring all the liquid over the chip and it's still connected to power and so on, and I was thinking, oh, what is he doing? But this is non-conducting, so there's no danger in doing that, even though, of course, there's a little danger when you anyway are touching the open machine. So, but that's why we let students do that. Okay, cooling it down for a while until it has a quite low temperature. Okay, we didn't measure the time now because this was just for taking the video. So what he's doing now, he's disconnecting the power here. There's no battery in here. And now to show that it's really powered off, he takes the chip out. We could now move it to a second machine. In our case, we put it back to the original machine. So what he has done, he has put another USB stick in there. You can, you might have seen it behind his head now, where here's a new stick with the cold boot operating system to be booted from. And you also see here the chip, it's really frozen, so it's very cold. Connecting power again. This took, if you would have seen the normal time, around 20 seconds between disconnecting and connecting again. And then the machine boots, and now he's turning it over any second. And here you can see actually this is this MS RamDump project program, which actually reads out the data, and this will now take a minute or so. And then we have all the data that we need, and we can analyze it offline. So the results that we had. You might remember this long list of modules that we investigated. We investigated all of them at different temperatures with different time periods for the power cut, and 5 times each, so that we have some statistical average. And this is what came out for DDR2 DRAMs. They were, in that case, 10 seconds without power at minus 35 to minus 30 degrees Celsius. And what you see here is, for instance, on the right-hand side, the error rates that we had. So byte error rates and bit error rates. So what you see here, that the bit error rates and consequently the byte error rates are quite low for some of the modules. The worst case we had was actually a kind of a third of the bytes being damaged in that case at that temperature. Similar results, and then we were surprised, we were actually getting data out of DDR3 modules. Not out of all 5, but at least out of 3 DDR3 modules. Same conditions, 10 seconds without power, minus 35 to minus 30 degrees, and we almost recovered all of the data in that case. So very low error rates. So if you look at the dependencies on the temperature, so this is for 100 megabytes test file and for different temperatures. So you have the temperatures here starting with minus 35 degrees, going up to kind of slightly lower than 20 degrees. You see that up to, almost 0 degrees, there's, this is the number of bytes and you had 100 megabytes, so this is roughly 1%. There's still below 1% damaged bytes in the dump. So that's quite good. And then there's an exponential increase of the damaged bytes with a growing temperature. So this is how the picture looked like at minus 35 degrees, minus 5 degrees, plus 15 degrees, and plus 30 degrees. There was almost nothing to see anymore. Same approach for different times. So this was at a constant temperature of minus 20 degrees Celsius, but now with a longer power disconnecting time. So if you have time, disconnecting time of, let's say, up to 40 seconds, or what do we know? Let's say up to 35 seconds disconnected time. So there's 1% error rate still only. So that means really the state is kept at that temperature for a very long time still in the RAM. Okay, so still good enough to actually extract the keys. What we also investigated a bit, we didn't have time for that at the end, so we will continue that later on, is that we saw error patterns. So particularly on some, not all DRAM modules had that, but many of the DRAM modules had this kind of striped pattern with the errors. And that is probably related to the ground state of the RAM. So when the RAM is initialized, you either have it completely with 1 bytes, completely with null bytes, or a mixture of both. And surprisingly, when you have this mixture ground state, there is almost no error in there. So the reason is not yet clear to us. We have some speculations, but I want to keep them for myself for the time being. Okay, so what can you do actually to prevent yourself from being cold boot attacked? So there's not so much you can do actually, because many of those solutions work only if the cold boot attack is performed on your own machine. If somebody takes your RAM out and moves it into a different machine, then, what can you do? So what you could do on your own machine is you can enable the power on self-test and BIOS. Most of those tests override the complete RAM at the beginning, at the start of the machine, then everything is deleted. Apparently that was not the case on the main boards that we used, so we turned it off. You could, of course, password protect your booting sequence. So usually people do this attack with a USB stick. If you password protect that, nobody has a chance to do RAM dump on your machine. You could do password-based pre-boot authentication. So again, some form of authentication before the machine is booted. And so you also avoid the encryption key to end up in the memory. Or you could store the encryption key outside the RAM. And there have been experiments where people have done that, for instance, using the CPU to store the keys. And that would actually also work if the RAM module is moved from your machine to a different machine, because the key is not on the RAM module, so it cannot be recovered by dumping the RAM image. Okay, that was basically it. Some conclusions. So what we saw is we were actually a bit surprised that cold boot attacks are not as complicated as we thought they would be. So it could really be a feasible approach, for instance, for digital forensic investigators to use that one. And we also saw that attacks on DDR3 are possible. So admittedly, we have probably had some big luck that we chose a board where this was possible, but still it works. Okay, that's it. Thank you for your attention. So I made us some time. Good.
That was in time and very well before time.
Yeah.
In spite of very little time you had, right? You had half of the time because we started late. So thanks a lot. I knew this attack by the name of Evil Maid attack. Yeah, Bruce Neer named it as Evil Maid Attack in his
Okay.
blog. Yeah, but I had voted for this talk to be here.
Ah, great.
So thanks.
You're welcome.
Thanks a lot. Any questions? Yeah.
So remember, your questions stand between us and lunch.
You have shown DDR2 memory which you are taking out from the laptop after cold spray and
Yeah.
taking into another laptop. But nowadays, the embedded latest DDR memories comes as a small single chip memory. It's not too big size. It's very small size. Even at you can get for 4 giga or 2 giga size. So just imagine an embedded board where the single chip DDR2 or 3 memories soldered. And my question is then how will you take it out or how will you do the same experiments on that?
Of course, if the memory chip is somehow hard connected to the board or somewhere, then of course this approach is very tricky to do. That's quite clear. So in that case, well, yeah, you have really to come up with some new ideas. Right. Okay, any other questions?
Hi. Actually, I wanted to ask, like, the image that it creates, is a DD image, DMP image, or an MEM image?
Sorry?
The image of memory that you create on a USB is which kind of an image?
It's a simply raw image.
Raw image.
Yeah.
Thank you.
So we had to search for the picture.
Any more
every time.
questions?
And have you tried to steal real encryption key? Not an image, but in real system. Have you tried?
Well, actually, this has been done not by us, but by Haldeman et al. They have. If you read their paper, it's really good. If you are interested in this, read their paper first because they did a very good investigation of all this, and they have shown, for instance, how they extracted keys from BitLocker and from TrueCrypt and so on and so on. And they were successful even though they had bit error rates up to 30%. With all the round keys also being still in memory, they were able to recover the keys.
So it works, and I can read it in your paper, yes?
Well, this is not in the presentation, of course, but there was this paper. Let me briefly go back. In the previous work, it starts with lest we remember. If you Google for that, then you will easily find it. So that was this paper, Haldeman et al.
How would you mitigate such an attack?
Yeah, that was what I had on one of the last slides. So what you could do, of course, is protect your own system against these kind of boot attacks. So trying, if somebody tries to boot from a USB stick, for instance, protect against that. That also, so to enabling this power on self-test, to overwrite the content at the beginning, at the boot process, for instance. But if you really have somebody who takes the chip out and the chip can be taken out because it's not soldered to the board or whatever, well, then you cannot really protect against unless you move the key out of the RAM to somewhere else. And there are several other solutions to do that. CPU was one example.
So the moral is don't keep your laptop powered on. Since Marco is here.
I know. Okay.
Any more?
So thanks for your patience.
Thanks, Marco. Friends, you can enjoy your lunch. We'll be back here in